and let me know when we are live.
Okay, I'm working on it. Wait a minute. Okay.
Are we live?
Yes.
Okay, great. Perfect. Let's get this started. Hi, everyone. Welcome to another lecture of this course, PNS Modern SSDs. We had a couple of research paper presentation during the past weeks, but today we're going to get back to another background lecture on modern SSDs, basically how modern SSDs benefit from advanced NAND flash commands to improve read-write performance. So yeah, let's have a very quick recap. We discussed about SSD organization in the previous meetings. That basically in SSD we have SSD controller that has a multi-core CPU with per channel flash controllers. We also have a DRAM to store metadata and also use for some other stuff like write cache or read buffer, as well as yeah, basically for all these internal operations of the SSD. And the size of that DRAM usually is 0.1% of the SSD capacity. And we also discussed about NAND flash chips, the hierarchy that we have, that basically we have several channels. In each channel, we have several packages, and per package, we can have several dies. In each die, we can have, again, several planes. And each plane, we have hundreds or thousands of blocks. And per block, we have tens to hundreds of pages. We also discussed about some unique NAND flash characteristics like erase before write, asymmetry in operation units like read program they are doing in the page sizes, and for erase that we are doing at the block sizes. And we discussed that NAND flash cells, they have limited endurance, and we have retention loss, and so on and so forth. We also discussed basic NAND flash operations, that how we do read, program, and erase. But today we're gonna look into some advanced NAND flash commands. And after that, we're gonna look into address translation, which is the basically is a result of these characteristics of NAND flash that we need erase before write. And we do this out of place update. And as a result of that, we need this address translation step and garbage collection. So we're gonna get into that hopefully today as well. Okay, so yeah, let's analyze the SSD performance a little bit. Basically, the latency or response time is the time delay until the request is returned to the basically processor. And we know that the average read latency for a page, like 4 kilobyte page, is around 67 microsecond. And these are coming from some data sheet that you can see basically the source from this link. And also the average write latency for a page is around 47 microsecond. So you can actually see that write is faster than read. And the reason is that whenever you want to do a write operation inside SSD, normally we write inside the DRAM buffer. And then we just, SSD just sends the acknowledgement to the processor, to the host system. And we don't really wait for that program, actual program happening inside the NAND flash chips. So unless we really need to do that, because at some point your write buffer might be full and you need to somehow wait, or there are also some requests that you cannot, by definition for those requests, you really need to wait until your data has been written inside the NAND flash chips. But unless in these cases, we usually have enough, we can actually write in DRAM buffer, and that's the reason that it's quite faster compared to read. So throughput is the number of requests that can be serviced per unit time. So we usually report it as IOPS, like the input number of input-output operations per second. So the random read throughput for this specific report is around up to 500K IOPS. And for random write throughput, we have up to 480 K IOPS, which is I mean, quite good when you compare it to hard disk drive. That I will show you the numbers very soon. And the bandwidth is the amount of data that can be accessed per unit time. Usually, when you want to calculate the bandwidth, you have the workload with sequential read data pattern. So for sequential read or sequential write, basically. So the sequential read bandwidth is up to 3,500 megabyte per second. And for sequential write, bandwidth is up to 1,300 megabyte per second. So when you compare these numbers to hard disk drive, you can see significant improvement compared to, I mean, in SSDs with respect to hard disk drive. So the latency for accessing data in hard disk drive is something between 5 to 8 milliseconds. The throughput is bigger than 1,000 IOPS, but you can see like 2 orders of magnitude, basically higher throughput for SSD, and the same thing for bandwidth. So you can see a large improvements for when we use SSDs. So now let's get back to some detailed parameters when we want to calculate the latency and throughput, basically. So we have some different timings in the NAND flash SSDs, and these timings can basically affect the whole overall calculation or overall latency of your access. So one of them is TR, which is the latency of reading or sensing data from the cells into the on-chip page buffer. So whenever you want to read a page from NAND flash chip, you send a command to your NAND flash chip, and it will take some time for that NAND flash chip to prepare your data internally in the page buffer, basically that placed inside the NAND flash chip. So we call that as a sensing time or TR, which doesn't basically include the latency that you need to transfer your data, your read data from NAND flash chip to the controller and to the host. It's just about the latency that you need to spend or the basic to have your data ready in that page buffer. We also have this tproc, which is the program latency with the data in the page buffer. So whenever you have your data, your page basically that you want to program it inside the page buffer in the NAND flash chip, it will take tproc basically to have your data written in that NAND flash chip. And we also have this TBRS, which is the latency of raising the block in NAND flash chip. So all these numbers, they vary depending on the MLC technology, whether or not we have SLC, MLC, TLC, QLC, and also processing node and microarchitecture. For example, in 3D TLC NAND flash chips, TR and T program and TBR, they are around 100 microsecond, 700 microsecond, and 3 millisecond, respectively. In addition to that, these are the latency for NAND flash chips. But in addition to that, we have also channel latency that we usually calculated using IO rate. So whenever you have your data inside the NAND flash chip and you want to communicate it to the host, or you have your data in the SSD controller and you want to communicate it to the NAND flash chip, for example, for doing programming, you need to go over the channels, and that channel has a limited bandwidth. So basically, the number of bits transferred via a single IO pin per unit time. So we usually use this parameter to calculate the latency. A typical flash chip transfers data in a byte granularity, like the 8 IO pins usually these days. And you know that basically pins are quite costly. So it's not really easy to increase the number of pins and provide higher bandwidths. So as an example, we have 1 gigabit IO rate. And if you want to transfer 16 kilobyte page size, the transfer time that we usually call it TDMA, it will take like 16 microseconds. So that's also the latency that you need to spend to transfer your data. So yeah, so now by doing all these numbers, let's get back to some calculation for normal read and write operation. So basically, when you want to do read, you need to, so we are using the same assumptions basically as we had before. So when you want to do read inside the NAND flash memory, you need to first send a command to the NAND flash chip. Then NAND flash chip will spend some time to prepare your data in the page buffer that we already discussed. We call it TR. And then we have TDMA, which is the latency of sending back your data that you were looking for to the controller. So in the flash controller, we need to do basically ECC decoding and also de-randomization. So imagine that, assuming that we can actually ignore the latency for sending command and also de-randomization, because these are actually relatively fast compared to other timings. So we can see that the read operation can take around 136 microseconds. And for program, basically, we first need to randomize our data, then we do ECC encoding, and then we need to send a command, write command to the NAND flash chip. And together with write command, we also need to send our data. So we need to do that transfer. So we have this TDMA, and then we need to do programming. So by summing all these numbers that we have, and again, we can basically eliminate T randomization and T command for simplicity. So we can see that the write latency can go up to, can go to around 736 microseconds. And similarly, you can also calculate the bandwidth. So now that you know that, okay, I will spend like 136 microseconds to read 16 kilobyte, and for read, and also I'm gonna spend like 736 microseconds to write 16 kilobyte of data, then you can actually calculate the bandwidth. So the problem that immediately we can see here is that the SSD read latency, SSD read bandwidth, SSD write latency, and write bandwidth, all of them are quite much different from these numbers that we just calculated. So we have much better performance for read as well as write. So we're gonna discuss a little bit today about different techniques and basically ways that SSDs are using to improve the performance. So, and these are optimizations techniques that basically SSDs are making. So first of all, to just give you some clue, in SSD, we have quite a lot of internal parallelism that we can benefit from these parallelism and improve the effective latency of your accesses, even though each basically SSD access can take some time. But when you're averaging, because you can service a lot of requests in parallel at the same time, then you can actually see that the overall effective latency is getting much lower. And also, as well as your throughput's getting higher. So we have huge internal parallelism inside the SSDs. We also have write buffer that I just discussed. That write buffer can be DRAM based. In modern SSDs, also this write buffer might be SLC, because so the backend of SSD, we may use actually TLC NAND flash chips like 3D TLC or even QLC. So with TLC and QLC, our NAND flash chips are quite slow. So there are some SSDs that they are using SLC write buffer. With that SSD write buffer, they can actually have a huge, much larger write buffer because they don't have the problems of DRAM, that DRAM is volatile and we need to back enough capacitors to make sure that we have enough charge to do that de-staging buffer. So yeah, basically with this write buffer, we can heavily improve read and write operations as well. So yeah, so I'm gonna talk about some other optimizations that we have, basically that we are making in SSDs to improve performance. One of them is like the advanced commands that we have for small reads. So minimum I/O units in modern file systems is 4 kilobyte. And in modern SSDs, most of the time, especially when your SSD is optimized for cost and I would say bandwidth, we are using the page sizes of 16 kilobyte. Just only for SSDs that they are optimized for access latency, we are using smaller page sizes like 2 kilobyte or 4 kilobyte or so. But most of the SSDs that we are using nowadays, they have 16 kilobyte page sizes. So if you send a request from your file system, which is 4 kilobyte, basically a page read, unnecessarily reads and transfers 12 kilobyte of data, and that can actually cause waste of bandwidth as well as also longer latency, because you wanted 4 kilobyte, but you need to wait for 16 kilobyte access. So there are a couple of optimizations that vendors are making these days. One of them is sub-page sensing that has been employed by Micron. So you can actually see, check the link below. So this is actually a microarchitectural level optimization that directly reduces TR. So when you have a request, so imagine that your page is 16 kilobyte and you send a read command to your NAND flash chip that you want to read 4 kilobyte. So this is called as sub-page sensing. So since your access is less than a page, then actually it can reduce the latency. So you will experience much faster TR in order to sense 4 kilobyte as opposed to sense 16 kilobyte. So that's one of the optimizations that basically vendors are making. Another one is random data out, RDO, which is so data transfer with an arbitrary offset and size. So imagine that, so you have your data after TR in your page buffer, but you don't really need the whole 16 kilobyte of the data that you have read. So you want basically 6 kilobyte of that, for example. So you can actually use this optimization, random data out, that you only transfer the part of your data that you needed. And it can heavily reduce TDMA and ECC, for example, for your basically access, and that can eventually cause faster read access. So these are the two optimizations that vendors are actually making. Another one is actually cache read command, so that we can perform consecutive reads in a pipeline manner. So in a normal way that we don't want to use cache read, we have this, we send read page A. So we need to spend like TR to have our data ready in the page buffer. Then we need to spend TDMA to send our data to the flash controller, and then TECC. So if we want to do another read, we can actually start it the moment that we have our data in the flash controller. So once we have our previous read ready in the flash controller, we know that our flash our channel is actually basically free. So we can send another read request to the NAND flash chip and then start the process. So by this, you can actually overlap reading and ECC with this by pipelining read A and read B, which is good, but we can do better. So we can also overlap TDMA and TECC by doing cache read. So with this request, basically, whenever you want to send base command A, you also send a command for reading B as well. So you send both commands together, or kind of cache read. So the second one is cache read. So once we are done with TR of the first read, we can actually start doing the read for the second read as well. So this can overlap TDMA and TECC, which can greatly improve the performance. But this needs additional on-chip page buffer, because previously you had only basically one read in the page of buffer, but now you need to have enough number of page buffers. So yeah, so basically when you do page read A, you have it in your page buffer 1 after sensing, and then you start sending out this page A to the flash controller. In parallel, you can also do cache read B, and the good thing is that you have a spare page buffer that you can use it for this request. So yeah, that removes TDMA from the critical path and increase throughput, bandwidth, and reduces effective latency, which is good. Another optimization is multi-plane operations that we haven't. We actually discussed it briefly in the past, but today we're gonna see more. So with multi-plane operations, basically we can do concurrent operations on different planes, as long as basically we have those requests are for this, they are doing the same operations on the same page offset. So basically the position of the word line that we are referring to should be exactly the same for all these planes, and the operation should be the same. So it shouldn't be like read for some of them and write for some others. So everyone should do the same operations at the same offset. So if you can make it, you can heavily improve the parallelism. I mean, improve the latency, like the effective latency and also the throughput by benefiting from multi-plane operations. So that actually adds huge overhead on the page mapping and also basically the SSD controller that we're gonna hopefully see next week. But today we assume that we can benefit from it. I mean, as whenever it's possible. So it can, as I said, it can increase the throughput bandwidth almost linearly with number of planes that concurrently operate. So the bandwidth with regular page program, when you want to program 16 kilobyte, as we discussed before, we need to spend like 736 microseconds, and the bandwidth is 22 megabyte per second. But if you can actually program, for example, 2 planes at the same time, so you need to program 32 kilobyte. So the latency of the programming, like the T-prog, is 736 microsecond, which is in parallel because, I mean, you are doing this operation in parallel. But you, no, sorry. So the latency of programming is 700, which is you will spend it in parallel. But you actually need to spend TDMA and TSCC serially. So you need to also add them here as well. So it's going to be 700 plus 16 plus 20 plus 16 plus 20 microsecond. But overall, since especially for writes, for programs, because the program latency is the dominant factor, so TDMA and TSCC does not really, affect the whole throughput much. So in the end, you're going to see a lot of benefit, and as we discussed, almost linearly performance. So now with 2-plane operation, we can get to 41.5, for example, megabyte per second bandwidth. And we can actually get better numbers as well. So this per operation latency increases because now you need to spend more data. So you need to spend more data for basically ECC encoding and DMA. But the T-prog stays the same. So if you can benefit from these, even though it increases the per operation latency, but overall it contributes to better effective latency and better throughput. So, and the benefits highly depend on the access pattern and FTL's data placement, whether or not it's possible to do multi-plane operations. And we're going to see that later, that adds a lot of complexity to page mapping in SSDs. Okay, so another optimization is program and array suspensions. So we know that read performance is often more important because writes can be done in a synchronous manner using buffers, as we discussed. And also a read request can be returned only when the requested data is ready, after reading the data from the chip. So basically reads on the critical path, and we cannot delay it much. So as a result of that, basically in many the scheduling techniques, we usually try to prioritize reads over writes, which can provide better performance. So the problem arises here that we have significant latency asymmetry. So the read latency is around 100 microsecond from the numbers that we discussed in TLC NAND. The T program is 700 microsecond and T arrays is 3 to 5 milliseconds. So assume 5 milliseconds here, for example. So this is a TLC NAND flash numbers. So yeah, and also remember that if the chip is designed to program all the pages in the same word line at once, the actual program latency is 2100 microsecond. So since this is TLC NAND flash, so you should be able to store 3 pages at the same time. And since the program latency for each page is around 700 microsecond, you need to actually spend like 2100 microsecond to program the whole 3 pages. So the problem here, you can see that the worst case chip level read latency can be 50 times longer than the base case latency. Imagine that you want to do a read and your flash chip is basically available. So you access your NAND flash chip and you do the read, and it will take like 100 microseconds. But in another scenario, your flash chip is busy with doing an erase operation. So you need to wait 5 milliseconds. And that's caused basically 50 times longer latency compared to the best case. So to deal with this issue, we have this suspension idea that we can suspend an ongoing program or erase operation once a read arrives. So let's see with this figure how it can help. So you have a ongoing program operation that will take like 700 microseconds. After 100 microseconds, you will receive another read. Imagine that we don't have this suspension, so we need to wait until this program ends, and then we start the read operation. So the latency that we observe here for the program is 700, and for the read operation is actually 700 as well, because it needs to wait for 600 microseconds and also another 100 microseconds for each read. So in the end, it's going to be 700 microseconds. But with this suspension, we can actually suspend the program whenever we receive the read, and we do the read operation. And then we start resume the program basically step. So the latency for a program is going to be something around 800 microseconds. For read is going to be something around 100 microseconds. So you can see that can significantly decrease the read latency as well as the average latency with this idea of suspension. But it also comes with some cons, which is additional page buffer for data to program. And also it complicates IO scheduling. So until when can we suspend ongoing program requests? At some point, it can cause some unfairness to write operations, or for example, to the applications that they have more write operations. So they can actually, at some point, they get slow down a lot because of all these suspensions. So actually, we discussed these things in a nice ISCA paper in 2018 that called Flynn. Hopefully, we will basically premiere a talk about that paper as well, that we discuss about how we can design a fair and high performance IO scheduling for SSD devices. And it also has negative impact on the endurance. So whenever you do this suspension and you want to resume, there are papers that they have shown that it has negative impact on the endurance. So yeah, I mean, even though it's nice, but it comes with some price, with some overhead. So yeah, so let's quickly summarize this technique. So we discussed about sub-page sensing and random data out. And also we discussed about cache read command, multiplane operations, and program and array suspensions. And all these techniques have been more or less actually basically taken and implemented in modern SSDs. Okay. So we have still some time, so I'm going over address translation and garbage collection. But before that, I will wait to see if there is any questions. Okay, good.
No question from YouTube.
Yeah, thanks a lot, Lenny. So let's have another overview again on flash translation layer. We discussed about SSD firmware that we often refer it to as an SSD controller. So it provides backward compatibility with traditional hard disk drive by hiding unique characteristics of NAND flash memory. And the SSD firmware is responsible for many important SSD management tasks, including address translation plus garbage collection that performs out-of-place writes due to erase before write property, wear leveling to prolong SSD lifetime by evenly distributing PE cycles or program erase cycles, data refresh that resets transient errors by copying data to a new pages, and I/O scheduling to take full advantage of SSD internal priorities. So today we're gonna start our discussion on address translation and garbage collection. Let's see, this picture provides a simple SSD architecture. So this is a storage view at the operating system level that is a flat block device. Here we consider like 16 blocks that we have. So each entry here is a logical block address. And in the SSD, we have some physical block addresses, as well as physical page addresses that you can see. You can see that actually here in SSD, we have a larger capacity or larger number of pages. So at the host layer, we had 16 logical block addresses, but here we have 20 physical page addresses. And that's the reason is that it get used, it can benefit a lot for the performance and lifetime of the SSD. We're gonna see a little bit later why that's the case, but yeah, but this basically extra or over provisioning capacity for SSD devices is really important. So let's take a look how we do write request handling and or basically this page write. So yeah, so imagine that we receive a request that we want to write a data, which we call it A here, in a logical block address A. And so the size is also 1 because, yeah, we want to write only one block, and the direction is also right. So yeah, inside the SSD, imagine that the early state, I mean, the initial step is that all pages are free. So the firmware will give us the first page, a physical page available in the block 0, and we just program data A in that block, in that page. So here we are assuming that logical block size equals to physical page size, which actually is not the case in many modern SSDs, but we're going to see in later lectures that how we can handle this I/O mismatch. But for simplicity here, we consider that logical block size are, equals to physical page sizes. So yeah, so after this writing program of A, imagine that we receive another request, which we need to do another write operation, starting from logical block address 4, and the size is 12. So it has 12 basically logical block address, and the direction is right, and then we have the payload of data. So yeah, so we may actually think here that SSD would give us this nice free block 1, block 2, and block 3, because actually the address also starts from 4. So we can actually nicely write this data from B to M to these addresses from physical page address 4 until physical page address 15. But in reality, it doesn't happen. And in SSD, we just continue writing from block 0. And yeah, and that's the way that we do it. And why is that? Because basically we have the problem of active block or write point approach. So we like to keep only one block being written at the moment. So this is due to the open block problem. So if you want to have several blocks open, like the write point at the same time, they can cause a reliability issue for the data that they have been stored currently. And also, we'd like to have this program sequence constraint that we have a fixed program order within a block. So we try to continue our writing on the same blocks, on the same block that we have. They are already open. So yeah, that's the reason that we continue writing to same block. And when we are done with block 0, we go to the block 1. And when we are done with block 1, we go to block 2, and then we block 3. Yeah, but now the problem is that we have basically logical block address that does not match a physical page address. So we need to fix it. So if we receive later on a read operation from logical block address 4, we don't know basically where it is stored. So we don't know basically where is this the physical page address. And that's the reason that we need to maintain this address mapping information. So we have this mapping table of logical page address or logical block address to physical page address. And in this mapping table, we store that logical page address or block address 4 is mapped to physical page address 1. And with that information, you can actually send a read command to the corresponding NAND flash chip and provide the data. And that's how it works. Now let's say when we receive some update. So later on, sometime later, we receive another write on the same logical block address that we had before, like 0. That we can call it actually as an update. So because you're updating the data that have been stored in the past. So basically what's happening is that, as we discussed before, we have this out of place update in SSD. So we write this data in a different page. Basically, we don't update the physical location because we need to do this out of place update, and we write this up prime on the next free page that is available. So here is physical page address 13, and we also need to basically update the mapping table that logical page address A is now mapped to physical page address 13. And we need to invalidate the physical page address 0. So yeah, assuming that we receive these updates like more and more, so we need to actually keep invalidating the previous location and validate the new one and update the mapping table. But at some point, we're gonna run out of free pages, and that's basically the place that garbage collection comes to play. So garbage collection reclaims free pages by erasing invalid pages. So here you can see that we have some invalid pages. And so garbage collection needs to reclaim free pages by erasing these invalid pages. So how is it done? So you know that erase unit is that block. So we need to have a victim block. So we need to have a block that we know that all pages in that block is invalid, such that we can easily just remove it. But we know that this is not usually the case. So we will end up having some blocks that they have some valid pages and have some invalid pages. So all the valid pages in that block, they need to be copied to other free pages to make that block fully invalid, and then we can erase it. So we call this block as a victim block. And it has huge performance overhead, garbage collection, because you need to do a lot of copy. And for each copy, essentially, you need to read from NAND flash chip. You need to, and then you need to program it in another location. So you're gonna have a lot of these read and program latency of valid pages. So you really want to minimize. One optimization is that we want to minimize the number of valid pages in our victim block. And it also has lifetime overhead because now you're gonna have additional writes because of these copying things that you need to do. And that can basically increase program erase cycle that you have. And this actually is called as also program amplification, that the number of writes that has been sent from the host is the number, but the number of writes that you actually have in your SSD usually is much higher compared to the one that you had, I mean, from the host. And that one of the reason is actually this copying that you have internally inside the SSD for garbage collection. So we can have actually different technique or policy to choose a victim block. But one greedy victim selection policy is that we erase the block with the largest number of invalid pages. So the block that has the largest number of invalid pages, hopefully, I mean, this block has the less number of valid pages, so we're going to have less copy data, basically copy overhead. But we're going to also see later that that's not the only optimization metric that aspect that you should think of, because it's also important that which bandwidths you can do the copy stuff. So if you can actually benefit from multi-plane operations during your garbage collection, that can heavily improve the performance of garbage collection. So yeah, so that's the reason we call it this policy as greedy, because it's only focused on one optimization metric here. It's based on the number of basically the number of invalid pages in the block. So in order to implement this greedy victim selection policy, we need to maintain the number of invalid or valid pages for each block. So for that, we have a status table in the flash translation layer that per physical block address, we keep the status. So here you can see that, for example, for physical block address 0, we have one invalid basically page, and we have 3 valid page. In physical block address 1, all pages are valid. And for example, for physical block address 4, we have 1 valid, and we have 3 pages free. So the status can be free, valid, or invalid. Free meaning that you can actually write to it. So yes, so that's the status table. So by checking this status table, you will see that block 3 has the highest number of invalid, basically, pages. So it's going to be selected as your victim block. There is only one basically valid page here, which is M. So you need to copy M somewhere to your so you will copy it to your write point, which is block 4. So you need to read the physical page address 12, and you will write it to another location in block 4 and in 17. And then so block 3 is fully invalid. And in also block 4, you have 2 valids and 2 free slots. And then you need to update the mapping. So here we're going to have some issues when we want to update the mapping, because so now we need actually the other way around of mapping. So we know this the physical page address here 12, but the mapping table we look it up from the logical page address. So how we can know the vice versa, like how FTL knows physical page address 12 is mapped to logical page address 15, unless it maintains physical to logical mapping as well. So the thing is that physical to logical mapping is stored in each physical pages out of band area. So as we discussed in the past, like the pages that we have, if they are like 4 kilobytes, the actual space that we have in that page is actually larger than 4 kilobytes, and we have some space to store some metadata for like this physical to logical mapping data, as well as ECC and some other stuff. So basically, you will store the physical to logical mapping in the out-of-band area in your pages. And using that, you will realize that basically physical page address 12 is mapped to logical page address 15. And with that information, you can actually look it up the mapping table and update the physical page address location of logical page address 15. So yeah, so once we update it, then we can actually do raise of block 3 and make it ready for future write. And then we can update the status in our mapping table that for basically pages in this block tree, all of them are free and they can be used for write. Here also, I like to mention that block erasure and a status update is done just before programming a new page to the block, which we call it lazy erase. So when block tree is we make block tree a victim block, meaning that all pages in that block, they are invalid, but we don't do the erase operation immediately unless we really need to do that. So we usually delay it. And the reason is that we want to basically, we don't want to have several open blocks in our NAND flash chip. So we want to, minimize the number of, or we want to have only one block ready to be written at the same time. So due to this reason, we actually we use this lazy erase approach that will delay the erase until we really need to do it. Okay. So let's get to some performance issues of garbage collection. So garbage collection significantly affects SSD performance because it has high latency. And in modern SSD, we have large block sizes. So there are several tens to hundreds of pages in each block. So assume the block contains like 576 pages, and only 5% of the pages in the victim block are valid. So which is not assuming, 5% is not that large, right? But even with this low number of, percentage of victim block, you're gonna see that we need to do copy of 28 pages. And so GC latency is at least basically this 28 pages copy, like TR plus tproc, as well as erasing, which is gonna end up 27,000 microseconds, which is a lot. So that you can see that's order of magnitude larger latency than TR and tproc. And also copy operations are the major contributor in garbage collection. So erasing latency is not really that, does not play much in the overall latency of garbage collection, but this copying operation is a very time-consuming operation. So if FTL performs garbage collection in an atomic manner, meaning that when SSD is doing garbage collection, it does not basically accept or service any requests, and it delays user requests for a significantly long time. And it can cause long tail latency that cause performance fluctuation in your SSD device, and also it can be used for some basically quality of service attack kind of. So when we have a read dominant workload that is running with a write intensive workload that has a lot of writes, so that write intensive workload will gonna basically cause a lot of garbage collection. And this read dominant workload, even though it doesn't really need that much garbage collection because it doesn't have a lot of writes, but it's gonna be affected by garbage collection. And it causes performance, fairness problem, as well as quality of service problem. So these are the issues that we can have with garbage collection if it's happening in atomic manner. But modern SSDs they are using some technique actually to avoid these issues as much as possible. Sorry. So one of the advanced technique is actually using trim or unmap or discard command. So this command actually informs FTL of deletion or deallocation of a logical block. So at the file system, whenever you, for example, delete a file, normally, at least in hard disk drive, so the operating system does not really inform the SSD that, oh, this data is not is already deleted, because that doesn't really need it for hard disk drive. But for SSD, it actually makes a lot of difference, because if file system does not inform the SSD about the deletion or deallocation of that logical block, SSD would consider that block or those pages as valid pages, and we're gonna keep copying these valid pages through the SSD to make sure that they stay there. But using this trim, file system can inform SSD about deletion of them, and that allows FTL to skip copy of obsolete data. So SSD can consider these pages as invalid pages, which can cause a lot of good performance. Another way is to do background garbage collection. So we want to exploit SSD idle time. Of course, now the question is that how to accurately predict SSD idle time. And there are tons of research actually in this line, doing some heuristic technique, some learning technique in order to, predict SSD idle time and do this background garbage collection. But this can be also a problem, because when you do this background GC, you may do garbage collection in prematurely, meaning that you copied pages. Those pages that you are copying, they could have been invalidated by the host system using trim command. So that can comes at some price of this overhead. But overall, I would say background GC is a very important technique that has been used in many systems. And another important technique is actually progressive garbage collection, which can divide GC process into subtasks. So FTL does not do garbage collection in an atomic manner. So when we need to copy like 28 pages, we, for example, copy one page, and then we service a user request, and then we keep going like that. So that can heavily reduce the tail latency of ongoing requests to your SSD. And and that's the main reason that actually if we profile the performance of SSD these days, we don't really see that dramatic slowdown in throughput or dramatic increase in your IO access time in modern SSDs. And the main reason is that modern SSDs, they have been, they are using this progressive GC, that they don't do this garbage collection in an atomic manner. So if you want to learn more about this topic, I would suggest that you check this paper in address mapping, DFDL. And also, there are also some other recommended material like cache read and retry from this paper from our group in ASPLUS 2021, as well as program and arrays suspension that you can look into them. Okay, so yeah, I think we are done with today's lecture. Are there any questions? So yeah, next week we're gonna basically go into garbage collection in a little bit more detail, as well as we're gonna discuss also about how we can do this fine-grained mapping, and basically the overheads that we have when we have this fine-grained data mapping, that we have this IO mismatch, basically, that the IO request, like the logical block size is 4 kilobyte, but physical page size is 16 kilobyte. And it can cause some issues that we're going to see hopefully next week. So yeah, so thanks a lot to everyone for paying attention to today's lecture. And yeah, and we're going to discuss next week. Thank you.
Thanks for the great lecture.
Thanks a lot.
I will stop the...
Yeah. So I'm going to leave the Zoom. Thank you, Lenny. Thanks, everyone.